Hello class, welcome to the second play posit for properties of solutions. We're going to explore colligative properties today. Specifically, we're going to look at Raoult's law and its effect on vapor pressure lowering. We're going to look at the boiling point, elevation, and freezing point depression processes. We'll look at osmotic pressure and electrolytes and their deviation from the Vant Hoff factor, which we'll talk about as well. There are two quests that align with this: solution stoichiometry and colligative properties of solutions. So, colligative properties. When we're talking vapor pressure lowering, this is Raoult's law, R-A-O-U-L-T, Raoult's law. The pressure of your solution is equal to the mole fraction of the solvent times the vapor pressure of the solvent. Essentially, this idea is as we add a solute to our solution, that solute dissolves, and the solute particles get in the way of the solvent particles from escaping the surface of the solution. So typically we see the vapor pressure of a solution will go down as more particles are dissolved in solution. This makes sense because they essentially block them from escaping the surface. We also have boiling point elevation, works with the same principle. The whole idea with colligative properties is that the solute is getting in the way. And so we want to look at how does the solute that we're dissolving impact the solution itself. So again, boiling point elevation, if we're boiling something, we're intentionally heating it to the liquid gas transition point. And as we add more solute to our solution, it gets in the way of those particles from escaping the surface, and you have to overcome the attraction of solvent and solvent, but additionally you'll have to overcome solvent and solute attractions. And since you have to overcome both of those, you end up elevating the boiling point and raising the overall temperature. Same deal with freezing point depression, it goes the other way. If you're trying to freeze, you have to overcome the solute and solvent interactions so that the solute can become more ordered, and it takes a lower temperature in order for things to freeze. If you think about the wintertime after or right before a snow, they tend to salt the roads. The whole purpose of this is so that those particles can dissolve in the water and prevent the roads from freezing, because the roads would have to get to a much lower temperature in order to freeze because the particles are getting in the way. We also have osmotic pressure. Osmotic pressure is, there's a typo there, sorry, osmotic, O-S-M-O-T-I-C, osmotic. Osmotic pressure, here we have the equation pi is equal to mRT, where m is the molarity, R is the gas constant, T is the temperature, and pi refers to the osmotic pressure in atmospheres. Sorry, I had to think about that for a minute. So pressure in atmospheres. Okay. Here we've got Kf and Kb, which are the freezing and boiling point constants. Those are solute dependent, so you might have to refer to a table. We've got M, which is molality. So like I said, we need to know about molality for that reason. And then delta T is the change in temperature. So let's do a calculation with Raoult's law. Calculate the expected vapor pressure at 25 degrees Celsius for a solution prepared by dissolving 158 grams of common table sugar in 643.5 centimeters cubed of water. And at 25 degrees, the density of water is 0.9971 grams per centimeter cubed, and the vapor pressure is 23.76. All right, so there's going to be some math we have to do, some stoichiometry here, but that is okay. The key here is that we expect to get a vapor pressure lower than 23.76 at the end of the day. We know that as we dissolve this sugar in here, it should cause the pressure to go down because less water molecules are escaping the surface because they are interacting with our solute. So first we need to figure out how many moles we have of our solute and how many moles of water. All right, so moles of solute, and we know we have 158.0 grams, and they give us the molar mass. Lovely. And I've pre-calculated it to save time. There are a lot of problems we got to get through, so we'll get 0.4616 moles. We also know that our amount of grams of water is going to be based off of this volume and the density. So 0.9971 grams per centimeter cubed, and then that will have to be multiplied by 8.02 grams of water per mole to convert this to moles of water. And we end up getting 35.60 moles of water in the end. Okay. If you really wanted to know the grams, we started with 641.6 grams. That was my in-between step. So I multiplied by my density, got 641.6, and divided that by 18.02 and got 35.60 moles of water. All right, so now I need my mole fraction of my solvent. So I need the 35.60 moles of my solvent over 35.60 plus the moles of my solute, 0.4616. All right, and this whole thing will be multiplied times my vapor pressure, 23.76 torr. And, oops, I end up getting an answer of 23.46 torr. So it didn't go down by much, but it did in fact go down, which is what we expected. The mole fraction calculation resulted in 0.9873 as my mole fraction, so I multiplied that times 23.76 torr if you needed to see the in-between step. Okay. All right. Now, actually, just to go back to this conceptually, let's think about it for a minute. There's only one particle being dissolved in here, that's sucrose. If we're looking at something that is ionic, remember that ionic compounds separate into their ions. So for every 1 mole of, say, NaCl, we would technically get 2 moles of ions because you have 1 mole of Na plus and 1 mole of Cl minus. That would cause a more significant effect on your vapor pressure lowering due to Raoult's law because you have more particles there. And in fact, we're going to look at some deviations later on based off of that idea. Okay, so here you go. This one, predict the vapor pressure of a solution prepared by mixing 35 grams of solid Na2SO4 with 175 grams of water. And they tell you the vapor pressure. So here's the deal. Like I said, we just talked ionic, so I wanted to prepare you for that. So Na2SO4 will split up into 2 moles of Na plus and 1 mole of SO4 2 minus. So in total, we're going to have 3 particles per mole. So when we figure out our moles of Na2SO4, we're actually going to need to multiply that value by 3 before we figure out our mole fraction. Okay, so 35 grams of my sodium sulfate, and let's convert that to moles. The mass I had down was 142.05 grams, and I got 0.246 moles of sodium sulfate. But remember, we have to multiply by 3 particles per mole to figure out our total mole of solute. So 0.738 moles of solute is actually being dissolved here when we look at each particle. Remember, each particle, each ion has to interact with the water molecules when they dissolve, and each ion gets surrounded by the water molecules. Therefore, dissolving something like sodium sulfate has more of an effect than dissolving something like sugar, which only has 1 particle. Remember, sugar is a covalent compound, and even though it may be polar, and still dissolve in a polar solvent, there's only one particle per mole, whereas here in ionic you've got more particles, therefore there should be more of an effect. So let's do Raoult's law again. We need our mole fraction. The moles of water, I haven't calculated that yet, oops. The moles of water, actually just to save time, I'm going to tell you the moles of water. 9.71 moles of water. Hopefully you calculated that and figured that part out. Because we had 175 grams divided by 18.02. Again, we've got a lot of problems to get through, so I don't want to waste time showing too much work. I can condense where I know you're capable. All right, and just show you the new stuff. 23.76, and that's our torr, right? And we end up getting 22.1 torr as our vapor pressure. And if we're comparing that to the previous slide, sure enough, there was more of an effect for sodium sulfate dissolving than for sugar because there were 3 particles as opposed to 1. The other thing to consider with that is that the particles dissolving in sodium sulfate might be a little bit larger, so that could affect also how much water is needed to dissolve those particular ions. Okay, so as I said, the next logical step is boiling point elevation and freezing point depression. The idea is that the particles get in the way, and so it prevents things from either boiling or prevents them from getting more ordered to freeze. You'll have these constants here for boiling point elevation and freezing point depression. They are solvent dependent. So depending on which solvent we're using, the values will change. I will show you a problem like that. And then we'll see several examples actually. So here's the first one. A solution was prepared by dissolving 18 grams of glucose in 150 grams of water. The resulting solution was found to have a boiling point of 100.34 degrees Celsius. Calculate the molar mass of glucose, and it's a molecular solid that is present as individual molecules in solution. That's key because it tells us there's only one particle. We're not going to have to multiply by anything funky like we did for that Raoult's law problem. Okay, so here's what we need. We need that equation, delta T equals Kb times our molality. Delta T is the change in temperature from the normal boiling point. So the normal boiling point for water is 100 degrees. So our difference between 100 and 100 degrees is 0.34 degrees Celsius. Okay? So remember, normal is, so this is our norm, 100 degrees Celsius. Okay? So I can rearrange my equation. I need to find my molality in order to find the molar mass. Okay? I need delta T over Kb for specifically water, right? So from that chart on the other side, I have found out that my Kb is 0.51. Units are Celsius, kilogram over mole. And this is over 0.34 degrees Celsius. So the Celsius will cancel, and because we're dividing by kilograms over moles, we'll end up in moles per kilogram as our answer, which is our molality. So we end up getting 0.67 as our molality here. Now, we know that our sample is 150 grams of water. So what we're going to need to do is figure out how many moles of glucose we have in our sample, right? This is per 1 kilogram. So we have 0.67 moles per 1 kilogram, but we have only 0.150 kilograms of water in our sample. So we're going to have to set up some relationships here. We know that the mole of glucose over 0.150 kilograms is equal to 0.67 moles over 1 kilogram. We cross multiply here. We get that N of glucose is going to be equal to 0.10 moles. And now we want to figure out molar mass. So we know that the amount of mass in my original sample was 18 grams. 18 grams divided by 0.10 moles. Again, grams per mole gives you molar mass. We're going to end up with a molar mass of 180 grams per mole for glucose. All right, so let's look at this one. A chemist is trying to identify a human hormone which controls metabolism by determining its molar mass. They weigh a sample of 0.546 grams of their hormone. They dissolve it in 15 grams of benzene, and the freezing point depression was determined to be 0.240 degrees Celsius. So what they did is they froze their solution. They saw that the freezing point was a little bit lower than the normal for that of benzene, and now they want to figure out our molar mass of our hormone. So let's do it. And I get a really large mass of 776 grams per mole, which is okay because if we think about it, we're thinking about a hormone, so like things with proteins and things of large mass, it makes sense that we get a large molar mass. Similar deal. This time we're looking at osmotic pressure though. So continuing with our biological approach, which is pretty cool. Hopefully the biosci folk will enjoy this. To determine the molar mass of a certain protein, they dissolved 1 times 10 to the negative third grams of it in enough water to make a 1 milliliter solution. So we're definitely working on a small scale here, using a lot of pipettes and things like that. The osmotic pressure of the solution was found to be 1.12 torr at 25 degrees Celsius, and we want to figure out the molar mass of the protein. All right, so this one we're going to use, since osmotic pressure, we're going to use a different equation, pi mRT, where pi is our osmotic pressure in ATM, so I know I'm going to have to convert this torr to ATM. Remember that there's 760 torr per 1 ATM. And then I'm going to need to plug that into my equation to figure out my molarity. And once I have my molarity, then I can figure out my concentration from there, or my molar mass from there. So 1.12 torr, again, to save you some time with the work, we end up getting 1.47 times 10 to the negative third atmospheres. And I want to plug that in. So I want to rearrange so that molarity is equal to pi over RT, which means 1.47 times 10 to the negative third atmosphere on the top, and on the bottom I've got 298 K and 0.0821 atmosphere, liter, moles, in Kelvin because it's my gas constant. All right. And when I multiply through the bottom and then divide top by bottom, I get 6.01 times 10 to the negative fifth moles per liter. And remember, I started with a 1 gram sample. So I divide my grams by my moles. All right, times 10 to the negative fifth molar. And I end up getting my molar mass of 1.66 times 10 to the positive fourth, 10 to the positive fourth grams. Okay, which is the same thing as 1660 grams. Again, looks large, but when you remember it's a protein, this is kind of small for a protein. Here's just a good visual of a pure solvent versus a solution. This is before they're at equilibrium. Once they come to equilibrium, this difference here is our osmotic pressure between the height of the solution versus the height of the solvent. All right, another good biological application. What concentration of sodium chloride in water is needed to produce an aqueous solution isotonic with blood? And they give you the pi, the osmotic pressure of your solution. Of course, blood, so it's going to be at relatively high pressure. So we've got 770 atmospheres. All right, and we want to figure out our concentration. So we've got same deal, M equals pi over RT. And when we plug that in, 770 ATM over 298 times 0.0821. I'm being bad and leaving units off. Don't do that, but I'm doing it just to save time. I know this is running long already, but I promise, all these things are interesting and we do need them. We got our total molarity. Now, remember, this is a total. They want to know the molarity of sodium chloride. So, because sodium chloride in solution is split up into one Na plus and one Cl minus, what we're looking at, since it's already dissolved, we're looking at how many moles from 2 particles, right? So this is for 2 particles total. In order to figure out the amount of sodium chloride before it's dissolved, we're going to need to divide that amount. So 0.315 moles per liter over 2 particles per mole, and we'd be able to get our, so 2 particles per NaCl, right? We'd be able to get how many moles of NaCl we need, which 0.315 divided by 2 would be 0.158 molar as our concentration of NaCl. So again, when we think about ions, we got to remember that they split up when they're dissolved, so that number does matter. Okay. Now the reason that number matters is when we're looking at the colligative properties of electrolytes, it changes what's called the Vant-Hoff factor. So the Vant-Hoff factor accounts for how many particles are dissolved in solution. If you're looking at your equation, so if it's a colligative properties equation, say freezing point, so Kf times I times your molality. I is your Vant-Hoff factor, tells you how many particles there are. If you salt the roads, a salt that has more particles per mole is better than something like table salt, NaCl, which has only 2 particles. I believe typically we use calcium chloride, which has 3 particles, CaCl2, when we salt the road. So for that reason, it's a better salt than NaCl when it comes to salting. So again, the number of particles in the solution divided by the number of moles of solute dissolved, basically just counting the particles. That's what it should be in theory. However, what we find out is that there are sometimes deviations that may occur due to ion pairing. Ion pairing is what's pictured here. You have a lot of particles in solution. It happens when you're more concentrated. When you're more concentrated, it's likely that the ions are going to get closer together. When they're closer together in solution, they still can have some interaction, and we form what's called an ion pair. So the more concentrated a solution, the more likely there's ion pairing, and therefore we'll get deviations from our typical trend of freezing point depression or boiling point elevation or osmotic pressure and even vapor pressure lowering. So we see deviations due to ion pairing. Okay, so our last problem says the observed osmotic pressure for a 0.10 molar solution of this lovely iron ammonium sulfate complex at 25 degrees is 10.8 atmospheres. Compare the expected and experimental values for I. So first I need to figure out how many ions this thing splits up off into. So if we're looking at that formula, I count 5. We know we're going to get some Fe ion. I imagine it's an Fe2 plus 2 NH4 pluses. Oops. NH4 pluses and 2 sulfate 2 minuses. Yeah, those charges add up. That makes sense. For a total of 5 particles. So typically I should be 5. We want to figure out what it actually is. If this solution's fairly concentrated, we could have ion pairing and therefore a deviation. So let's look. We know that I is equal to I times MRT, because now we're looking at an ionic solution. We want to rearrange. We want I is equal to pi over MRT, and we know that our pressure is 10.8 atmospheres, and then we've got 298 K times 0.0821 times our concentration of 0.10 molar. Okay, that's an M, 0.10 molar. And when we get our answer, we get an answer of 4.4. So the Vant-Hoff factor has decreased, and if you see so this is experimental, if you see a decrease Again, likely due to ion pairing. All right. Now, even though a 0.1 molar solution isn't very concentrated, you have to remember that with this particular complex, that you get 5 particles for every 1 mole. So the fact that it is just a very large complex and you get a ton of ions could contribute. The size of those ions could contribute. They're going to get closer together because there's more ions, and it's likely that we will have a deviation. All right, that is all for today.